Alrighty, so number 37 here. First up, you're going to want to go ahead and graph this function that they have, the p equals 2000 over 1 plus e to the 5.3 minus 0.4t. Kind of a confusing function, but you can just go ahead and either plug it into your calculator or some graphing thing online, and you can go ahead and graph it. And once you graph it, you'll see that this slope kind of continues in this upward pattern here. And so I wouldn't say that it ever levels out. The first question is, does the population level off? No, not really, because we have this continuous slope that keeps growing, and if it were to continue on this pattern, we'd keep getting a line like this, and it doesn't look like at any point it levels off. It doesn't do that. So for B, it says estimate when the rabbit population grew most rapidly. All right. It says how large was the population, how large was the population at that time. So the slope continues to increase, so the population continues to grow more rapidly. All right, so what does that tell us? Basically that I would say that the time where the slope is the steepest is when it's growing the most rapidly. So maybe in here it gets the most steep, and so I'd say right around in there is the time when it grows most rapidly. And so what we're basically trying to do is we could take the derivative of this function, the slope, and see where the slope, basically the derivative continues to grow more rapidly, where the slope is really steep or where it's continuing to increase a whole lot, okay? So let's move on to part C. In part C, it says what natural causes could lead to the shape of the graph P, and I say this, the slope continues to increase, okay? And that's because the population, the population of the rabbits, they continue to grow, right? It's just continuing to increase. So I would say maybe the only natural causes would be some sort of death factor. These rabbits are continuing to grow, but as new rabbits come, other rabbits die off or whatever. And so that could be some sort of, some sort of natural cause that leads to the shape of the graph. All right. So basically, what natural causes? Well, death could change that, or some sort of, maybe their habitat or like their food was affected in some sort or something like that. Those could be different natural causes that lead to the shape of that graph. Okay. All right, so I think this is our last problem. Oh, we have one more, I think, after number 39. Never mind. So number 39 says find the value of a so that the function has a critical point at x equals 3. Okay. So we can go ahead and take the derivative and set that equal to 0, but then we want to go ahead and plug in 3 for x, because we're basically saying, what a value would make it so that this x stuff, what a value would make it to where we have a critical point at x equals 3, and if that's what we want, then we go ahead and plug in x equals 3 and set the whole equation equal to 0. So I go ahead and I do that right here. And then all we would have to do there is solve for a. Okay, so of course we'd subtract, the 3a, e to the 3a over to the other side and do all the different algebra that it would take, but I kind of want to challenge you to be able to try to do that stuff on your own. Because all that stuff is just kind of algebra, and I want to make sure that you can kind of do that on your own. Let's see. But the calculus part of this is, you got to take the derivative and set it equal to 0, and it wants to know whether there is a critical point at x equals 3, so we just plug in 3. All right, moving on to the last problem here. We have number 43, and it's asking us, which of these three graphs, we have A, B, and C, which correspond to what? The graph of the function, the derivative, and then the second derivative. And if we see here, graph A has, like, let's see, it has what? Like 1, 2, 3 curves to it, okay? So that's some sort of like x to the power of like 3 or 4 or something like that, okay? And when we take the derivative, this exponent gets smaller, right? Because we have to subtract by 1 when we take the derivative. This would be like 3x squared. So the derivative function would have less of these little curves because it's an x squared, okay? So then we look to something that has the next amount of curves, and we see that B has 2 curves. It goes kind of like this and then like that, okay? And so if there's 2 curves there, we know that that's a less order, or it has a smaller exponent, and so we know we're moving down in exponents, so that means we must be taking derivatives. And so then this B curve here would be the first derivative, and then we move down in order even further. If we were to take this derivative, we get like 6x, and so there'd be, maybe only like there would only be like 1 curve, and this should start out as a 4, and that should be a 3 or something along those lines, and then this would end up x squared, and then we'd have, I'll draw C in a different color so it's easier to see, but we'd have just kind of like 1 curve here, and that's like an x squared kind of thing. So we're moving down in order, the exponents are decreasing, so we know that the one with the most curves has to be the first function, the original function, and then as we go down in the amount of like waves that we have, we move kind of down in derivatives, okay? Alright, so that concludes 4.1, and we'll go ahead and do 4.2 tomorrow. Okay.